Now that we've walked through all the geometries, I want to share how to actually use VESPR theory when we talk about problem solving. Usually, what we're doing is we're trying to convert a chemical formula into a picture of what a molecule looks like in space. And so, the first step is always to draw that Lewis dot structure and understand it. Then, from there, we apply VESPR theory. So, I'm going to continue my very first example, which was ammonium. Here we go. Sorry. So if I wanted to get an idea of what this molecule was like, and that's going to involve its geometry and then later polarity, how it would interact with water or oil, I'm going to start with its Lewis dot structure always. And so what we found when we walked through our Lewis dot structure kind of to-do list is would look something like this. Now I'm going to try to build a 3D picture of this molecule rather than this two-dimensional one. So first I'm going to count all my electron pair domains, my lone pairs and my bonded pairs around the central atom. And so here I have just one central atom, so it's kind of simplified. It's just a nitrogen. And I have one set of lone pairs, and I have three things that are bonding to that central atom. So I have 4 electron groups or domains, whatever you prefer. So now I'm going to arrange those domains or electron groups to minimize their repulsions. So I need to get 4 things as far apart from each other as possible. And so that's going to be about 109 degrees, but I know it's going to be distorted more than that. And so that distortion is going to come from the lone pair. And so what I'm going to do then is try to identify the geometry that this will be. With 1 lone pair and 3 bonded atoms, this is going to be trigonal pyramidal. And my bond angle is going to be a little bit less than 109 degrees. And I can then name that geometry, and I can draw this now in 3 dimensions. The way I would draw it is with my lone pair, and you might want to put it in a lobe, something like that. And then I would have my hydrogens. And the way I represent things in 3 dimensions is with wedges and dashes and straight lines. And so there is, chemists are not necessarily artists. In fact, many of us are not. And so we have, of course, like everything, created a set of patterns that are easy to reproduce that can communicate where things are in space. So perspective. If you are an artist, you may take this further and make it beautiful, but I will teach you the way to do it like a chemist would, which is not so beautiful. And so then taking that 2D picture and drawing it into 3D. So here is another example of CH4, and this right here is my Lewis structure. And this is my 3D picture based on VESPR theory. And what I do is I need to convey my bond angle is about 109.5. So I'm trying to replicate this picture on a 2-dimensional piece of paper, which is tricky. So we use wedges, dashes, and straight lines to communicate which plane we're talking about. So our straight lines are always going to be in the plane of the paper. So that means if I was to take this and slice it down the middle like this, I would be able to have 2 atoms that were in that same plane of the paper. And I would have one that came forward and one that went behind it. So you can see maybe like this, plane of the paper. I know the little video probably isn't the best. So my straight lines are right here, and they're just saying like, it's a carbon, a hydrogen, and a hydrogen, and they're all in the same plane. And then going into the paper is whatever is my hatched wedge. So my line. So right here. So this means that's going away from me. It's going into my computer or into my paper, whatever I'm working with. And then finally, I have solid wedges. These are coming out at you. So anything that's the solid wedge, so right here, I've got one going to the hydrogen. That's coming out of the plane of the paper to me. And so if these 2 that I'm holding in my fingers are in the plane, then the wedge would be represented by the one coming out, and the dashes would be the one going back. And so in that way, I can create something that has a little bit of perspective that shows this picture in 3 dimensions. And it takes a little bit of practice. Another aspect of this that takes a little practice is putting it all together for a larger molecule. It's easier to do with very small molecules with one central atom, but I expect you to be able to apply these to molecules that have more than one central atom. Here's a favorite, caffeine. So it's an example of a larger molecule that has lots of central atoms within its interior. So I'm going to go through and just highlight all those central atoms, things that are, and when I say that, so central atom really means bonded to more than one thing or 2 or more other atoms. And these are ones that we will assign a geometry to for each, rather than just one geometry name. The geometry of caffeine is like blob, right? So the carbon here, 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 and here are all central atoms. They are bonded to more than 2 things. Same with this nitrogen and this nitrogen here. And so I would be able to describe geometries at each of these. And I can look at them in 2 dimensions and count the number of things bonded to them and the number of lone pairs they are and predict that geometry using VESPR theory. I can then also draw it in 3 dimensions as I'm trying to show right here. And so this carbon with 4 things, this would be tetrahedral. And I would expect it to have about 109.5 bond angle. This carbon right here is attached to only 3 things. So I'm going to expect it to be trigonal planar with a bond angle of 120 degrees because it doesn't have a lone pair. This nitrogen right here is bonded to 3 things plus 1 lone pair. So I'm going to expect it to be trigonal pyramidal with a bond angle of about, or let's say less than 109.5 degrees. And then we have more of these trigonal planar carbons here and here and here. And we have another trigonal pyramidal nitrogen right there. So I'm going to have to work on this for each individual central atom.